Hi, everyone. Welcome back to the Protocol Labs Research Seminar Series. Thanks for joining. Special welcome to those of you joining from outside Protocol Labs or watching this recording online. If you want to be informed of future seminars or stay up to speed on what Protocol Labs research is doing more generally, you can visit research.protocol.ai and drop your email in the footer to sign up for announcements and quarterly newsletters. You can also find a playlist of previous seminars on the outreach page of our website under public talks. Also, if you have a suggestion for a speaker or topic that you'd like to see, please let us know by opening an issue in our public research repo. You can go to github.com/protocol/research and open an issue using the template provided. Today's speaker is João Antunes. João is a software engineer at YLD, and he recently completed his master's degree at Técnico Lisboa. His master's thesis work is in Pulsarcast. He was co-advised by David Diaz, who is head of the Resilient Networks Lab at Protocol Labs. So we are very happy to have him. His work is very near and dear to our heart. João, I'll let you take it from here.
So, as Jonathan so eloquently just presented up there, so my name is João Antunes. I'm a software engineer at YLD, and I've recently graduated from Técnico Lisboa, did my master's over there, and this is the work that I did for my master thesis, which is Pulsarcast, scalable and reliable pub-sub over peer-to-peer networks. So exciting, let's get this started. So let's start by our motivation. So what motivated our work? And in order for us to actually address that, we actually need to look at what is pub-sub, like why is it a thing and why is it useful? So pub-sub is a communication paradigm where you've got multiple producers and multiple consumers of content communicating in an asynchronous fashion. You have this full decoupling in time, space, and synchronization. And this is because essentially producers don't need to be blocked on the consumers of content. They don't need to know each other. They don't even need to be online at the same time most of the times in order for content to flow from one side or the other. And the fact that this property, like if you look at these properties, they're super interesting, right? Like they present these huge asset that of course a lot of tech companies look forward to use. And nowadays the way we communicate and the way a lot of the push notifications are forwarded to us and all of that is most of the times due to pub-sub. However, when you look at the whole of pub-sub and the technologies that are put in place, we can, if we put them in two buckets, which are the centralized pub-sub solutions and the decentralized pub-sub solutions, we can see this clear gap in between those. So usually centralized pub-sub solutions commonly lack the capacity to scale and have the data throughput that the decentralized pub-sub solution usually has. But on the other hand, a decentralized pub-sub solution commonly lacks in terms of reliability, consistency, delivery guarantees, and other sorts of guarantees that are commonly associated with centralized pub-sub solutions. And this is to motivate our work essentially. So the goal of Pulsarcast is a peer-to-peer pub-sub solution that is focused on eventual delivery guarantees, data persistence, scalability, while also trying to leverage the network infrastructure and protocols that are already in place. We don't want to essentially be recreating the wheel in terms of network protocols that are already out there. We want to take advantage of what already exists. So what we ended up creating, to start with, we created Pulsarcast itself is a spec, okay? So is an efficient and reliable peer-to-peer pub-sub topic-based protocol that anyone can implement according to our spec in any language of their choice. We also created a set of distributed algorithms and data structures that, again, anyone can use for any kind of purpose. But because we wanted to show that Pulsarcast actually works, we created a JavaScript implementation module of Pulsarcast, as well as a distributed test runner and a test suite to prove that, again, what we did actually worked. And one pretty relevant thing is that all of the work that we did over here is actually open source. Like the master thesis itself, the documents, the modules, all of that is open source. So the links are in here in the footer, but I'm happy afterwards to share through whatever medium everyone prefers. So when we started addressing this problem, the first thing you had to do, of course, is look at what's already in place, what's already there that we can use as a foundation for our work. As I said, as it goes with any kind of academic work, usually you want to look at what's already in place and build on top of that knowledge. And that's what we did over here. So we kind of split our related work into three big topics. So we have pub subsystems and we have web technologies. So pub subsystems, of course, may come like as an obvious choice for a topic to look into. Of course, again, we're doing a pub subsystem, but why web technologies? So remember that we were trying to come up with something that uses the network infrastructure that's already in place. And because of that, it makes perfect sense for us to look into web technologies and look at what the web has to offer to us. So starting with pub subsystems, we devised a set of design dimensions that provided the basis for the taxonomy that then we used to classify said pub subsystems. So this is the design dimensions are the subscription model. So essentially, are we speaking about a topic-based pub subsystem, a type-based pub subsystem, or a content-based pub subsystem? So, and what is this, by the way, like topic-based, content-based? So, in a topic-based pub subsystem, subscribers to content end up subscribing to like categories or like chunks of content that are just grouped within a specific tag, so to speak. So imagine you're interested in sports, you would subscribe to every single piece of content that is relevant within the category of sports. If you're looking at, for example, something like a content-based pub subsystem, you would be, it would be a lot more powerful because you have the possibility to actually define what you want based on the content of the message that you're getting. So if you, for example, are interested in like stock exchange kind of data, you could say that you're only interested in purchase orders that are above, I don't know, like $2 or something. And that is like the actual content of the message. In terms of the network architecture, you can, this is usually, there are the two poles, of course, like centralized and decentralized, and then, but you have stuff in between. So like in the broker-based network architecture, what happens is you don't have like this central point of communication. Instead, you have a network of nodes that act as brokers for traffic within the network. So like there's this no central point, but it's also not a fully decentralized solution. And then speaking about decentralized solutions, of course, we need to look into the overlays that they built. If they're relying on some kind of overlay and network overlay over here, so we're speaking about what is it? Is it a structured overlay like DHT? Is it a structured overlay like Cyclone, for example, which is one of the papers we actually looked into? And then we have like these two broader categories, which are subscription management and event dissemination, but are essentially the most important ones, which are how users subscribe to your content and how events are disseminated across the whole network. So looking at implementations specifically, so we have for the topic-based systems where, for example, Scribe, we looked at Bayo, Terra, and more recently stuff like Pulsarcast and VKPS. For type-based systems, which is actually something I haven't covered in the previous slide, I'm sorry about it, but type-based system is just essentially like if you grab the topic-based system and you put a type scheme, a programming type scheme on top of it, you end up with a type-based system. And such an example is Hermes. On the content-based field, you have stuff like Griffon, Jedi, Sub2Sub, Sienna, and others. Specifically, now moving to the web technologies, we can't actually speak about the web without addressing JavaScript nowadays. So JavaScript is ubiquitous, it's running everywhere, thanks to Node.js and NPM, of course. On the side of this, you also add a series of new network protocols that start to facilitate peer-to-peer communication. And then, of course, you folks over at Protocol Labs and IPFS specifically are more than acquainted with it. And then new peer-to-peer applications and tools that leverage all of the above, such as IPFS, the P2P, or browser cloud.js. So with all of this in mind, we eventually landed where we wanted, which is we needed to describe our solution. We needed to come up with what we wanted to do with Pulsarcast. So again, Pulsarcast is a peer-to-peer pub-sub topic-based system focused on reliability, eventual delivery guarantees, and data persistence. In terms of its architecture, so under the hood, Pulsarcast makes use of two network overlays that power the whole system. So the core overlay, so to speak, is the Cadimla DHT, because it's based on that we actually build the other overlays. And the Cadimla DHT provides this structured overlay that acts as a basis for peer discovery and also for some parts of content dissemination. But then the core of the content dissemination actually happens within the Pulsarcast overlays that are built based on the Cadimla DHT. Sorry. So these overlays are actually an overlay. Again, it's not only one overlay; it's an overlay per topic. So hence why overlays. And we usually call them actually dissemination trees, because these end up being trees through which all the content is disseminated for a specific topic. So essentially, the author of the topic ends up being the root node for said tree, and then all of the nodes underneath are either broker nodes or nodes that are subscribed to that specific content, that specific topic. When one of the core properties of Pulsarcast, and then what actually gives it its properties and its core properties, are the use of distributed data structures that we have. So we have an event descriptor and a topic descriptor. So each of these actually correlates to events and topics. And we make use of immutable data structures that the Merkle DAG has to offer, much like much like IPFS does under the hood. So essentially, each one of these structures can be referenced through an unique identifier, which is generated based on its content. And we make use of the links that you can have within the content itself to link to relevant structures. So what happens is, for example, for an event descriptor, you actually have two links. So one link to a previous event within this event dissemination flow, and another Merkle link to the topic it refers to. On the topic descriptor, on the other hand, we have a Merkle link for a previous version of said topic. So remember, we're dealing with immutable data structures. If you, for example, wanted to change something about this topic, so some of its configuration, and we're going to look at that in a couple of seconds, if you wanted to change something, you need to create a new structure like this. So whenever you did such thing like that, you would just point to the previous version, you would get like a nice history, so to speak, in terms of topic descriptors and what changed across the time. Another link that the topic descriptor supports is links to subtopics. So you can point to topics that you think that are relevant within this specific type of content, essentially. So if we put everything together into direct acyclic graph, you end up with something like this. Okay, so over here we have the events, which point to a previous event within the chain. Then the events themselves point to topics, and topics can have pointers to subtopics. The topics also point to previous versions of themselves. So the idea is that, again, you get a nice history feature on top of this. Looking at the detailed schema for both topics and events, we actually took advantage of the immutability that we were using here, at least for the topic, and we were able to actually inject configuration within the topic itself. So the topic is able to describe stuff like who's allowed to publish, and if there's some restriction in terms of who's allowed to publish, you can also allow other folks to request to publish message on their behalf. And another thing that you're able to do is actually dictate how the events are linked, essentially. So how these links between events are made, you're also able to configure that within the topic descriptor. As for the event descriptor, it's pretty much straightforward as it was in the previous slide. Essentially, you have, again, links to the parent, links to the topic that it's referring to, and then some metadata, payload, of course. And yeah. So moving on to the actual subscription management. I'm sorry, I think my AirPods may be losing battery. Do let me know if you stop hearing me. But yeah, getting back to the matter at hand. So subscription management. In terms of subscription management, so Pulsarcast uses quite a straightforward process, and that's why we rely on academia. Okay. So what happens is whenever a node is trying to subscribe to new content, what it does is it actually recursively at each node starts by getting the topic descriptor. With the topic descriptor, if you remember correctly, you're able to tell who's the author of it. And based on that author peer ID, what the node does is it recursively locally finds the closest peer to the author, so within its current state of the academic ADHD, and sends a join request to the closest peer that he knows about. And then, as I was saying, recursively, this process goes on. And as I was saying previously, you can even have nodes within this dissemination tree, which again are not even part of, or better yet, they weren't subscribed to the content, but now they became brokers for the content. Okay. So yeah, this is essentially an overview of the whole flow brought together. So again, you have the topic descriptor being found out over there, and then you have like the dissemination tree being built. In terms of the actual event dissemination, if you remember correctly, we allow configuration within the topic that dictates this. So we have two possible scenarios over here out of a multitude of them. They're essentially both ends of a spectrum. Okay. Remember that we have built the dissemination trees already. So for whatever is worth it, once you publish something, it's a matter of just disseminating content either to your parents, children, or both. However, given that we allow stuff like request to publish, or not all, in some cases, like not all nodes are allowed to publish, you end up with stuff like this, which can give you some properties, which is, for example, order guarantee. So if only the root topic, if only the root node for a topic is allowed to publish, you guarantee that all of the events will be published within a specific order. And when you resolve these links, you'll get the content again, all in the same order. Over here, we have the example where you actually allow custom event linking, and custom event linking is nothing more than just allowing the application that uses the underlying Pulsarcast model to dictate how the events are actually linked. So in terms of the actual implementation, again, we took advantage of lib P2P. So Pulsarcast by itself is a JavaScript module, and we made use of the lib P2P node and all of the properties that it has to offer, like addressing peer discovery for us, transports, and the Academic DHT that we rely upon. Just a brief overview of what essentially Pulsarcast is. It's just a class again. It provides this set of methods, and these again are some of the also more relevant classes to us, which are peer, the train, and topic node. But again, this is mostly implementation details, but feel free to dig into the code base if you're interested in. So moving on to how we actually test this. So one of the things we wanted to do is have the ability to actually easily deploy and test different versions of our module. We wanted to, of course, extract relevant user metrics, and we wanted it to scale to a large network, but we also wanted to simulate network constraints. And of course, we needed to automate this and kind of instrument it in a way where we could control everything from a central point and then inject our messages and inject our test runs, essentially. Once all of these things come together, it kind of became obvious to us that we needed, so reproducibility would address a lot of the things that we had in question. So like the ability to scale and the ability to deploy different versions of our software. And usually, nowadays, you get that through some kind of virtualization. And the lighter way of virtualization nowadays is through containers. And that's what we relied on. We relied on Docker containers. And to orchestrate said containers, we relied on Kubernetes. So that way we were able to scale to as larger network as our budget had to offer. In terms of the network constraints that we wanted to induce, there exist a lot of tools. So Mininet is one of those, and then like a couple of sister projects, so to speak, which are like Mininet, the ContainerNet, and Maxinet, all of them kind of related. However, they're super, super powerful, but they do a lot more than what we really wanted. You're able to do a lot of L2 and L5 things. You're able to create your own switches, routers, all of that, and we wanted something super light. We didn't really want something like that. On the other end, because we were in the Kubernetes land, you can also take advantage of service meshes such as Istio, but Istio on the other end only offers these kind of things for, and unfortunately only for the layer 7, so HTTP fault injection essentially. So what we ended up creating was a custom testbed. So the testbed itself consisted of an IPFS fork with Pulsarcast integrated. We relied on Docker to create these reproducible deployments, as we said, Kubernetes to orchestrate said deployments. And then to simulate the adverse network conditions, we relied on a really, really fun project, which is ToxiProxy. And what ToxiProxy essentially does is use lightweight TCP proxy that provides an HTTP API so that you're able to configure what they call toxics, which are essentially faults on the fly. You're able to inject latency and other kinds of fun stuff within your network. So essentially ToxiProxy and IPFS ended up making like the testbed deployment bundle that we deployed within our cluster. And then we relied on an ALK stack to extract all the metrics that we needed, aggregate those, visualize, and then again analyze them. So what, in terms of the actual data set we used to evaluate our system, so we relied on a data set, or better yet, a sample of a data set of ResNetLab. It's a total of 25,000 comments that we used as events and 23 subreddits that we used as topics. Essentially, we can see here the distribution of the topics and the events. You have, again, this follows like the kind of real world distribution that we wanted to achieve. In terms of test runs that we came with, so we wanted to extract two types of metrics, of course. So the first one was resource usage. So we wanted to know how much CPU, memory, and network our solutions were using. But then the most relevant to us, of course, is the quality of service. So the events are being published per topic, the events are being received per topic, and then something which we ended up calling the percentage of subscriptions fulfilled, based on two different factors. Okay, and this is important because we wanted the percentage of subscriptions fulfilled based on the events successfully published and the events that we actually injected in the system. And this is because for Pulsarcast, these two can be different. Because if you remember correctly, on an order guarantee kind of scenario, you can have nodes requesting to publish, but the content is actually only published when it lands on the root node. And whenever that content is actually published, it's actually also persistent. You can email the HT, and then you can rely on the event links to solve messages that you're missing from the feed, okay? We also looked into the number of RPC messages sent, just for, again, control sake. And we devised a total of 6 test runs, okay? So one where Pulsarcast runs on a normal condition, everybody is allowed to publish. One where Pulsarcast has order guarantee, and FloodSub, which is the P2P and IPFS own PubSub solution. At the time, I know that FloodSub is here, but it wasn't something that we could rely on initially for tests. And we did this with and without network latency added. So these are some of the results. And this is for Pulsarcast with where everybody is allowed to publish. And if you look at the event fulfillment comparison by topic, it is clear that Pulsarcast clearly outperforms FloodSub, where in terms of received messages and the expected in terms of the actual event fulfillment across all of the topics, from the most popular ones to the least popular ones, you can see a clear difference between both. So over here, and of course over here and over here. If we look at this in terms of percentage, it becomes quite clear, the distinctions between both systems. Where in FloodSub, we were only able to fulfill 45%, and in FloodSub, it's actually, sorry, in Pulsarcast, it was actually 99%. Now, for the rest of the data, we brought this together on a table. Now, it is important to highlight that for a huge chunk of the test runs, actually, probably half of the test runs, we ended up hitting limits within our clusters, actually. So for example, Pulsarcast with added latency and order guarantee, we had some nodes that crashed due to memory limits within the cluster. We didn't have any more memory to offer them. However, if we put the comparison side by side with FloodSub, we can still see that Pulsarcast, even with adverse network conditions, perform better than FloodSub, and it's also usually lighter. So in terms of memory, of course, data transmitted, because FloodSub is flooding the whole network, and CPU usage the same. So yeah, in conclusion, PubSub systems are vital for the distributed applications and the kind of work we do nowadays. And Pulsarcast tried to focus on 3 core properties: so persistence, reliability, eventual delivery guarantees, stuff that it's not usually associated with peer-to-peer solutions, but that we think it makes sense for it to exist, that there is space within the offerings that exist for something like Pulsarcast. And finally, our implementation performs quite well, compared to what is currently implemented, the native P2P FloodSub solution. Provides and it ends up providing even better quality of service. And finally, just a couple of thank you notes. So to my advisors, Luís Veiga and David Dias. There was also a colleague of mine, João Tiago, who was working on his master thesis. within the IPFS ecosystem, same as I, and like, again, really helpful. Even for emotional support, he was there. Whenever we wanted to cry, it was pretty useful. Finally, NESH, which is a research facility here in Lisbon that does work together with Técnico Lisboa, my faculty. And finally, Microsoft Azure for supporting the infra needed to run our tests. And finally, to you folks, the IPFS and the P2P community, for being so open to this kind of work, and for being here today, listening to me speaking about this boring stuff. So yeah, questions?
Yeah, not boring at all. So thank you so much. If there are questions, go ahead and jump right in, or you can put a hand in the chat if you'd like, or you can type your whole question in the chat if you'd prefer not to be in the recording, and I'm more than happy to read the questions.
Hi, so I have a question. Really great work, well done. I would like to get your thoughts on the overhead that PubSub protocols incur, and what was your line of thinking when you made the design decisions you made, and which eventually showed that, of course, your approach is better than FlatSub. So in FlatSub, for example, we've seen in one of your results, you have, delivery failures, basically. I suspect that this is because the bandwidth needed by the network is so big that, queues get overflow and eventually some messages get forgotten. Which is not supposed to happen with flooding in general, but in a real system, you can't keep messages, message memory forever. So yeah, just your general thoughts on how you went about evaluating, not evaluating, but making design decisions with regard to overhead of the protocol.
Yeah, so actually that's a really great question. Because one of the things, so if you look at the scope of the work that we did, like one of the things that we immediately did was this core design decision, which is we're going with guarantees and we're keeping the, and we're keeping the real timeness and the fast delivery, we're keeping that out of the equation. It was essentially, it came out as again, something that we kind of felt that was missing within the realm of solutions that existed for peer-to-peer networks. I'm not saying like that there's probably other work that does something like this. I'm not, however, like there's a clear opening for stuff like this, and we kind of felt that a lot of the work that exists within the peer-to-peer realm is usually like probabilistic, relies a lot on gossip-based protocols, and you're just trying to stream the content as fast as you can. But again, you're incurring the penalty of you're not sure if everyone will receive that set content. And that was like a clear design decision that we made. And that of course can be seen like it's not something that's actually covered within our test runs, but for example, for a test run with induced latency, in terms of our implementation, like we ended up unavoidably we ended up like creating a back pressure system. So what this meant is our test runs actually for Pulsarcast ended up with latency, with induced latency, ended up like lasting 4 hours because again, we're making sure that everything is persisted, that everything is being pushed through the network. Of course, you'll have a penalty with this, as with everything. And we also incur, of course, in a small penalty in terms of memory usage. Right now, these test runs didn't persist nothing within the disk. We made use of memory only. Yeah, that was essentially the kind of technical decisions we went through, and we weighted everything, and that was the penalty that we were happy to incur to provide the set of guarantees that we ended up providing. Actually, you were mentioning also the flood subtest scenario, and you're correct. So, but it was actually a set of two different reasons. So one of them, of course, was network flooding. Like in some cases, bandwidth wasn't even available, and the other cases was just an outspoken resource usage that ended up having our scheduler killing a couple of flood subnodes. So in some scenarios, like 20 to 30 flood subnodes were killed. So yeah.
Okay, very interesting. Yes, that's what I wanted to hear, your thoughts on this exactly. Thank you.
Pitar, I think I saw your hand.
Yeah. Hi, so thanks, awesome talk, very nice slides. I have a couple of questions. So one is, my understanding is that once you form a topic, the events are being distributed along a tree. And my question is, aren't you worried that this creates a single point of failure in case basically any of the nodes in the tree disappears, everyone below them can never get the messages?
Yeah, so we added in, it wasn't really covered in here, but we added in, actually I'm actually not 100% sure if we added in a redundancy mechanism where you actually, you always knew the neighbors of your three, so like your parents and children, you ended up knowing the neighbors, and if by some means you weren't able to forward content, you would connect to the other neighbor, because that was one of the initial ideas. But now that I'm thinking about it, I don't think we implemented that way. What we did is, if by any means the dissemination didn't happen, what we do is we just rejoin the topic because we already know the author and we are able to do so, and we go through the same process yet again. I'm sorry if, like, for this, because I was trying to think, because there was like this initial proposal, but it didn't end up happening. And to be clear, this is something that we, of course, feel like it makes sense to maybe improve in the future. But the core of the guarantees that we provide with Pulsarcast is through the immutable data structures and the links that I provide. So the idea is we embrace the fact that you may, I'm trying to, okay, I'll have to go through here for some reason. So we kind of embrace the idea that, oh, maybe too much, sorry. We kind of embrace the idea that these dissemination trees will kind of fail, okay? And the core concept of Pulsarcast is that you're able through, sorry, yeah, this is it. That you're able through these event links that you'll be able to, whenever you receive some flash content that points to an event that you don't have knowledge of, you're able to, again, reach out to the network and ask for said content.
Oh, so you didn't mention that you can actually ask for content.
Oh, sorry about it. Yeah, but right now that that ask for content is only is super reliant, and it's only built on top of Academia DHT. Because every time you're actually publishing something, that event is also persisted in DHT. So you have the ability to, again, through these links, then this is like the core property of Pulsarcast. I'm sorry if it isn't like, this is essentially the whole point of this talk was to describe this thing, and if I didn't do it correctly, my job here was not done properly, and I'm sorry about it. But yeah, the core property of these links and like the actual use, like the use for these links is for this said purpose. All right. So whenever you receive an event, so imagine you were out of the network for 3 hours for whatever reason. You rejoin the network, you get a message, and then through that message, you're able to, again, fetch content from the network, specifically from the Academia DHT, fetch content from the network through all of these links until a point where you're happy with what you have, or you just like fulfilled the gap in state that you had.
Let me ask, actually, my second question was related to this. So what you're describing now is basically so you're saying, well, if I join in later, I get an event and I realize that I don't know any of its parents, so I can ask about the parents because they are described in the event. Now, there's a little caveat here, right? Which is that what if I join and there's no more events? I just missed a bunch and there's nothing to hold on to.
True, and that is something that we haven't addressed yet.
So like a question, why did you go with a design that events have the parent link embedded in them as opposed to just a sequence number, and then you could just ask for sequence numbers, so you never need to an event to get started?
So the core, I'm trying to see if I can. Okay, so you're essentially proposing another idea, which would be you get a sequence event between events, and a sequence ID. Sorry, just a number.
Sequence on every event, because my understanding is that somebody from the tree publishes, but the root is the one that synchronizes the events and creates these links between them.
So not really. Again, that would depend. That will be upon the configuration that you. That will be upon the actual topic configuration that you actually provide. Okay. So the scenario over here in the right, every node is actually able to publish. However, this doesn't give you the same properties as this scenario over here, where you get the order guarantee, because again, only the actual topic root node is able to publish. Okay, so in here you get the synchronization that that said root node provides, but you get, of course, you're reliant on this single point of failure that we haven't actually addressed. This is something that our work didn't cover. And of course, you actually have a lot more round trips going on in terms of messages being disseminated through your tree. So this is actually the kind of configuration that you're able to inject in your topic. Okay, so you're able to dictate who's allowed to publish, if people are able to request to publish. So if by some means you make use of this allowed to publish list, you might be of your interest to support requests to publish from outside nodes, and then you actually can also dictate how the events are linked. So to actually answer your question, that may be a scenario where you could apply it if you're only dealing with this scenario over here, where the idea was to get some kind of order guarantee and only the root node were to publish. But our usage is a bit more broad, so you're able to get this scenario over here, but also other scenario usages. And also, like, you would lose the kind of immutability properties that you get with the usage that we have over here, where you always know, like, all of these DAG is immutable, so you aren't able to tamper with the content by itself, unless or if you tamper, so to speak, users could eventually realize that they've been tampered with the content. We don't support signatures though. Like, that wasn't something we also addressed within our work, but again, maybe something that makes sense or not. That's why we have this metadata open kind of description over here, where you're able to add more things if needed be. I hope it kind of answered your question.
Yeah, it does. This picture on the right makes sense. So basically about the event parenting. Definitely answers. Thank you.
No worries.
Okay, any other questions?
So
all right, I'm going to go ahead and stop the recording. Thank you so much. This was a great talk, and you're very gracious to forgive my butchering of your name as well in the beginning there.
No worry. I'm super used. Like, this is what I tell everyone. I'm super happy with as long as I turn around my head whenever I hear someone shout my name, I'm happy with it. I don't expect any non-Portuguese speaker to be able to say my name. It's unattainable. Nobody can do it.
Well, it's great to have you. We're really excited to see where this work goes, and thank you for sharing it with us.
thank you very much for having me. Again, thanks a lot for this awesome community that allowed me to do this kind of work.